Today we will talk about built-up beams, and we'll calculate shear in bolts that connect pieces into a built-up beam. So as shown here, this is a example of a built-up beam. So you can see that two plates, piece 1 and piece 2 are connected to the web 3 through a bolt. So this is called built-up beams. In previous examples, we always assume that these flanges and the web can be connected or bonded perfectly to each other as the interfaces. Right? We can use glue, we can weld them, but here in this section we will use bolts and fasteners to connect them together. So that we call them built-up beams. And what is shown here is a more practical case. Here you can see the C-shaped beam members are connected to two plates through two rows of bolts. Okay, so these are called built-up beams. We'll start to talk about this concept from the previously introduced case 1. Okay, we'll start from reviewing case 1. Okay, here is the case 1, a beam segment subjected to internal bending moment at section L and R. So this is section L and section R, right? So we should be very familiar with this case. So we analyze the stresses and forces which one of the flange, or this left flange, this flange is subject, one of the flanges is subjected to. So is it subjected to shear? So this is what we will analyze, right? What is denoted by the green color thing here is the interface. So as we analyze that, the interface on the interface you will have a shear pointing left. Okay, please recall how did we analyze this case? Okay, so first of all, we cut the flange out, right? And then we analyze its bending stresses, right? The bending stresses, if you still remember, on the left hand side it's subjected to bending stress like this. On the right hand side you have a larger bending moment. Right, so as a result, the resultant force delta F is pointing right. So you will have a V generated on the interface pointing left to balance the delta F. Right, so how did we derive the shear equation? Do you remember that? So the delta F can actually be calculated as the right pointing stress sigma R minus sigma L times A, right? This is the delta F, right? So we can extend it into delta M D over I times A, right? And we also combined the dA into a Q, right? Then this equation can be rewritten as delta M Q over I. Right, so here we calculated the delta F. Then to calculate the tau on the interface, on the green colored interface, the tau will be just a V over area of the interface, then the V equals delta F, right? So we get a delta F over A interface. And so here you get delta M Q over I over delta X times T. Right, the T is the thickness, and delta X is just here, the AB. Right, this is delta X. So rearrange it, you will get delta M over delta X times Q over IT. Right. And here the delta m over delta x is just v, it equals v, right? So we got vq over IT. This is how we derived this shear equation. Right? So in this case, we assumed that the flange is glued perfectly to the web, or the flange and the web belong to a integrated piece of material. However, in practice, the flange and web may be not bonded perfectly, but they are connected by bolts and fasteners. So the shear will not be carried by the whole interface, but the bolts. Right? In this case 1, the shear is carried by the entire interface. But if you are not using glue, you're using bolts to connect these pieces together, then only the bolts will carry the shear. Okay, so here is the difference. When did we talk about bolts? If you still remember, in early chapters, we talked about bolts and we talked about shear, single shear, double shear, etc. Please recall your memory, and we will use them later. Okay, then we will look at a lead-in example. So here, a beam fabricated by bolting together 3 wood members is subjected to a concentrated force P, and the bolts are spaced. This is something special here in this type of problems. Okay, the bolts are spaced at intervals of s equals 4 inch along the x-axis of the beam. Then you know other dimensions, TW, TF, HW, HF, etc. Okay, those numbers had been marked on this drawings, on the figures. Okay, then we have 2 steps. Step A, determine the shear stress in each bolt. If the bolts have diameters of d and are spaced at intervals of s equals 4 inch. Then the step B will determine the required spacing between the bolts if the shear stress in the bolts is limited to 5 ksi. So obviously there are 2 types of questions. The question A is an analysis question. You're calculating, analyzing the stress in the bolts, and the part B is a design problem. Okay, so this is analysis type of problem, and the B is a design type of problem. Okay, so then we will just do them one by one. Let's look at part A first. So you know the dimensions, you know the P, and then we need to analyze the stress in the bolts. Okay, so first of all, what we needed to do for the first step. We need to find V, I, etc. Those constant parameters, right? Since anyway, if you want to find the tau values, what is asked here, determine the shear stress. If you want to calculate the shear according to a normal algorithm, we need to use tau equals VQ over IT, right? So you need to know the V, you need to know the I, Q, etc. Right? We need to determine those parameters so that you can calculate the stress. So the first step, we need to find out the V value. Right? So here, as you can see in the loading, it's a simply supported beam subjected to a load P at the mid span. Right? So easily you can find the support on the forces on the 2 supports, the reactant forces will be half P. So the V values will be constant, right? Will be just half P. Right? This is easy to do. You just need to do a easy analysis. Then you can draw the V diagram here. So you will see the V equals half P. That is 17/2, 8.5 keeps. Then the second step, we will determine y bar and I. Right? Again, I believe you know how to use those two tables to calculate these two values. Okay, I directly give you the results. Y bar equals 3.32 inch from top, and I is 195.8 inch to the fourth. Okay, then step 3, we'll determine Q. But which Q are we studying? Are we calculating? Okay, so here is the interface. The interface has been shown here, right? And we have nodes dimensions. So actually, what we're calculating is the shear at these interfaces. So if you want to calculate the shear on this interface, normally we just need to cut this area or this area. Right? It doesn't matter. You will get the same results. Right? This to do this Q, then we just need to know A and D, right? So the A of each of them will be 2 times 4, right? So 2 times 4, you get 8 square inch. Then we need to calculate D. So what is the D value? D in this case, you have the global. You have the global centroid, that is 3.32 as shown here, 3.32 inch from top. Let's see it here. And the local centroid is here or here, right? So the D is right here. So our D value is actually y bar minus half of the height of the flange, that is 4/2. You get 3.32 minus 2, you get 1.32 inch. Then we'll easily get the Q, that is AD, 8 times 1.32. You get 10.56 cubic inch. And now we have no V and Q and I. Then seems that we can calculate the shear, right? So in this step 4, we will try to calculate the shear. Tau equals VQ over IT. Can we use this? Can we use this equation? Do you know T? Obviously, you know a T, but we can't use this equation since this equation was derived based on assumption that perfect interfacial bonding. It's if we can assume that the interface is a perfect bonding, like in glue or welding, we can use this equation. But now we have only bolts connection, right? We have only bolts to connect these two pieces. It's not a perfectly bonded, entirely bonded interface, right? So we can't use this equation because it's not perfect It's not a perfect and entire interfacial bonding. However, the shear force can be calculated as in our case 1. Okay, since the shear force is just calculated by balancing the delta F. Right? Since the delta F was recall in case 1, our V value equals delta F equals delta M times Q over I. Right? So this is still valid. Right? So the shear flow, we can also calculate shear flow this is, remember the unit of shear flow? Right? The shear flow, that is pounds per inch. Right? That is a shear force per unit length. Right? So shear flow, according to its definition, can be calculated by Q equals delta F over delta X. Right? So from the above equation, you get delta M Q over delta X I. Right? What is this? Delta M over delta X, that is V, right? So again, we got a VQ over I. So this is the equation we used last time to calculate Q, the shear flow, right? So from here, we can use the numbers given in this problem to calculate the shear flow. Right? The V is 8.5 kips times the Q is 10.56 cubic inch over I. The I is 195.8. So you will get 0.458 kips per inch. Then in the next step, we can calculate a shear force carried by each bolt. Right? We can calculate shear force carried by each bolt. Since we're requested to determine the shear stress in each bolt. So if you can calculate the shear force carried by each bolt over its cross-section area, so you get the shear stress, right? So we're calculating the shear force carried by each bolt here. So how to do this? The V pin, so each pin or each bolt carried shear force, so that is the overall shear force over number of bolts. Right? So if you know the shear for the overall shear force and you know the number of bolts that are carrying the shear force, this you can easily calculate the shear, the shear force shared by each of the bolts, V pin, by this, the overall shear force over the number of bolts. Right? So this is a logical equation. And it's actually still valid if you add per unit length above the line and below the line, right? Per unit length. right? So this equation will still be valid, right? So here let's look at what is the shear force per unit length. What is the shear force per unit length? Okay, that is Q, right? Shear flow. And what is number of bolts per unit length? Number of bolts per unit length. How do we calculate that? Since we know the space, right? The space between the bolts, that is S equals 4 inch. So this number of bolts per unit length can be calculated by 1 over S, right? The unit length over space between bolts, right? So here we will get the equation that is QS, right? The Q is the shear flow and S is the spacing between bolts. Okay, this is a constant when you design this a built-up beam, right? So here the V pin can thus be calculated as QS. So this is our equation, right? We just derived, and it is 0.458 kips per inch times 4. You get 1.832 kips. It seems that the rest of the problem will be easy enough, since you already determined the shear force in each bolt. So now we can calculate the shear stress carried by each pin, right? It's just V pin over area, cross-section area of the pin. So that is 1.832 kips, we just determined, right, over the A. So what is the A? It's a bolt, right? This is A pin equals pi D pin square over 4. Right? This is pi times the value is the D value is here, right? 0.75 square over 4. You will get 0.442 square inch. Here you get 0.442. So the shear stress can be calculated as 4.15 KSI. Okay. It's KSI. Okay, so this is the result of the part A. Okay, we just determined the shear stress in each bolt given the diameter of the bolts and the space between between bolts. And the part B is a design problem. Right? It's to determine the required spacing between the bolts if the shear stress in the bolt is limited to a allowable stress that is 5 KSI. Okay, so how do we design this problem? You can review the 6 steps we used to analyze the stress in the bolt. Right? Step 1, determine the V. Step 2, Y bar and I. Step 3, determine Q. Step 4, calculate tau and Q. Right? Calculate Q. Then step 5 is just calculate the shear, and we derived this equation V pin equals QS. Right? So which equation can you use to design S? Right? We still need to use this equation. Right? We still need to use the derived equation in part A. Right? Then everything will be clear. if you design this built-up beam, design the S value, the first 4 steps will be the same, will be totally the same. Actually, the first 5 steps will be the same. Okay, you just repeat step 1, step 2. It's 1 to determine V, like 2 determine Y bar and I. Step 3. Step 3 determine Q. And step 4, it determine the shear flow, right? That has been calculated as 0.458 kips per inch. And in step 5, we derived the equation. Right, this is V pin equals QS. And it's an inverse problem to the part A, since in this problem we know Q, right? We know Q, but not S. So we're designing the S. So the last step, number 6, is we know that the V pin equals QS, and this value is smaller, not larger than the allowable shear stress times A pin. Right? We can easily get this equation. Okay. Then to design this S, we just need to make sure that the S is not larger than allowable stress times A pin over Q. Right? So then here you get 5 KSI. This is the allowable shear stress given in part B, times A pin that has been determined in part 1 and part A, right? That is 0.442. Is that 4? Yeah, 0.442 square inch over Q, that is 0.458 kips per inch. Okay, then you will get 4.82 inch. So just to design this built-up beam, you just need to make sure that your space between bolts are not larger than 4.82 inch. This is the final solution. Okay. So through this lead-in example, we can summarize the steps, the algorithm, or steps to analyze or design a built-up beam. The first several steps are totally the same. Step 1, determining the V at the required section. Step 2, determine Y bar and I. Right. Step 3, determine Q. Step 4, determine shear flow in the section connected by the bolts. Right. These are the familiar steps. We already know these equations. Then we can we know that this equation will be used anyway, right? So the V pin equals A pin times allowable stress. Then you can design, you can do the analysis. Well, you can do the analysis of stress, or you can design the fastener space using such an equation. This is the equation we used in the lead-in example. The V pin is larger than QS, right? But here, just you can see in this general equation we added an M. This is the additional parameter. It's the number of fasteners or number of bolts in each row times the number of surface at which the fastener is being shared. Okay. So sometimes we need to multiply this V pin by an M, and this M depends on the setup of the built-up beam. Okay, in the next slide, we'll give you several examples to determine the area you need to consider the Q, you need to consider in calculating Q, and the M values. Okay. You can see the M is the number of fasteners in each row times the number of surfaces at which the fastener is being sheared. Okay. You can see in this case, you have these two components connected by one row of bolts, and the one surface will be sheared, one surface will be sheared, so the M value is just 1. And in this case, also you have just one row of bolts and one face will be sheared, so the M is 1. So in the rest of these examples, you can see here, the first one, when you cut the area, you can see that you have 2 rows of nails, right? 2 rows of nails. So the M is 2, right? 2 rows of nails and only one face will be one surface of them will be sheared. So M equals 2. And in here, this example, again you have 2 rows of nails, so the M equals 2. And here, 2 rows of bolts, so M equals 2. And here, 2 rows of bolts, M equals 2. Right? And here, 2 rows of nails, so M equals 2. And in the last example, this is a little special. Since at the first glance, you will see that you have 1 bolt, but 2 surfaces will be sheared, right? But when you're calculating one of the interface, when you cut this area off, you have just 1 row of bolts and 1 face will be sheared. So the M equals 1, right? Not 2. Okay, this is a special case. We will have an example later to talk about this. Okay. Then I can give you more examples. Like regarding the M. Okay. So we have seen that if you have such a built-up beam, there's 1 pieces connected by one bolt. So obviously the M equals 1. Right? Then how about if you have 2 components connected with 2 sets of bolts, 2 rows of bolts? Then M equals what? 2, right? Then in such a case, that 4 pieces are connected, and you have bolts here, you have bolts here, and when you consider this area, then the M will be 1 or 2 rows of nails, right? M equals 2. Then if you have these 4 pieces of materials be connected in such a way that you have 2 rows of nails, and on each row you have 2 faces will be sheared. So what is the M? 4, right? So later I will give several specific examples to illustrate all of these theories, how to use these theories to solve practical problems.